Good morning and good afternoon to everyone. And thank you very much for joining the webinar today. Today's topic will be sheet metal design with BricsCAD Mechanical. The presenter for today would be myself, Sagar Thurat. I'm the technical lead for Asia Pacific Brics, and our panelists for today who would be answering the Q&A will be Arvind Tunga, a senior support engineer working here at Brics. To begin with, this is in general the agenda for BricsCAD Mechanical, and our topic today would be sheet metal design, and we would just take a quick look at how sheet metal design fits into the entire mechanical workflow. Initially, I would like to proudly introduce to you Brics, a part of Hexagon PPM. Brics or BricsCAD are the global providers of cost-effective modern CAD, BIM, and MCAD solutions and common data environment products brought to the market under the BricsCAD brand. There are 500,000 Brics users in about 110 countries today. We are headquartered in Belgium with 200 plus employees in 12 countries. We have development centers around Europe, and in Asia, Singapore acts as the Asia Pacific headquarters and a product development center for BricsCAD. In the last 2 to 3 years, BricsCAD has globally expanded its market, and today it has offices in all the major countries, including countries like Hong Kong, Korea, the Middle East, India, whereas BricsCAD has always been present in these countries. Partners have been offering BricsCAD as an industry solution for over 10 years today. And since 2002, BricsCAD was available for the entire industry. Some of our clients and collaboration partners include the likes of Hitachi, Taiko, Mazda, Hyundai, Bosch, Nippon Steel, Prototype, Takamiya Construction, HOK, McConnell Dowell Construction. Mazda being one of our most important customers based in Japan and having global users of BricsCAD. Mazda connects 2D and 3D, and originally it is known as its innovatory rotary engine technology. Mazda Motor Corporation has become one of the premier automakers in the world today. BricsCAD solution family starts from the basics of 2D and takes you all the way to BricsCAD Ultimate, which is a fully functional vertical solution for AEC and manufacturing industries. And today our topic will be BricsCAD Pro and Mechanical combined for sheet metal design. What is the BricsCAD Advantage? BricsCAD offers you a one-stop solution for all your design needs, starting from 2D drafting, 3D modeling, and mechanical design. Our manufacturing solutions for product design and manufacturers are part of an entire ecosystem which facilitates industry collaboration and high-level design functionalities for manufacturing and mechanical industries. BricsCAD is the right choice that aligns with your 2D drawing and documentation standards. Over the years that you have developed your CUIs, XTP files, Lisp routines, ARX routines, VBNet scripts, your sheet sets, DWG, DWT files, plotter setups, all that you know on your current DWG platform can be directly utilized inside BricsCAD. Some of the largest customers, some of the largest companies in the world trust BricsCAD, such as Subsea 7, has deployed over 1,000 users of BricsCAD, and this is one of the largest success stories of BricsCAD. After 28 years of using AutoCAD, following a quick and easy installation, the team of Subsea 7 could easily transition to BricsCAD within a short time frame. So the core functionalities starting from BricsCAD Pro to Mechanical for the manufacturing industry include 3D direct modeling, 3D parametric modeling, associative drawing views. And for assembly design and creation, you could use top-down approach or bottom-up design approach depending on the user preference and the project type and the scale type. We include parametric standard design paths, materials, and mass properties as part of the software. Materials and mass properties can also be defined for your mechanical components. Bill of materials and balloons can be extracted and represented in the drawings directly. Automatic disassembled views can also be generated of your assembly designs. And sheet metal is directly integrated inside the mechanical workflow, which includes flange by flange design functionality, lofted bend functionality, convert to sheet metal, automatic unfolding, and batch processing to your CAM software. So design fully in 3D using BricsCAD and generate 2D technical documentation from 3D data. Create sheet metal parts design that are resilient. BricsCAD is free of the conceptual errors that plague history-based MCAD modeling systems bring. Your designs can be modified without the worry of failure because we combine the freedom of direct modeling with the power of feature-based design. So we will begin today and explain to you in the software how you can start creating a sheet metal, a very simple sheet metal from scratch, doing automatic unfolding and exporting it to DXF. Some of the features we'll be discussing is analytical unfolding, automatic junctions, bevels, tabs, thickness per body, tabs on curve, and bend radius. So these are some of the features that have been launched in the V21 version of BricsCAD. So I would directly like to take you to the software interface now. So this is BricsCAD. Users who are used to a CAD-based environment would be easily able to adapt to BricsCAD, as BricsCAD saves everything in DWG format. Clearly, right from the 2000 version all the way to the 18 and the 20 versions. And BricsCAD also imports multiple file formats and models right from DWG to Rhino, SketchUp, IGS, step files, SolidWorks, Parasolid, Creo, Inventor. Files can directly be opened inside BricsCAD for further modification and design. And you can also export your models as Collada, lithography for 3D printing, SVG, IGS, STEP, CATIA, IFC, and of course DWG and DXF is a standard save as. All right, so let's move now to sheet metal. Sheet metal is part of the mechanical functionality inside BricsCAD. So inside BricsCAD, you can do 2D drafting and design, 3D modeling, mechanical, and BIM. So if you put the mechanical tab on, you will be able to start doing your mechanical design. So let's begin with a very simple rectangle. For example, we can start with a 0, 0, 0, and just draw a 155 by 250 base flange, for example. Okay. And you could directly also change your design length, for example, like this. Okay. And this now you can see is the boundary detection feature, which will enable you to directly extrude, or you can create a base flange from this polyline. When I create a base flange, I get an option whether I would like to locate the line on the top, bottom, or in the middle. let's say if I accept this, your base flange gets created, and immediately your mechanical browser gets activated where this base flange is identified as a unique body. Okay. So we can start by pulling these edges. For example, I could first hide this polyline. So I can directly go here and hide the polyline here that was used to create the base flange. And then we can highlight this edge, and directly my quad cursor will allow me to convert this to a standard flange. For example, in this case, I will simply move this to 30, and the angle I can define. If I want to have another angle, I could do that, or simply keep it at 90, and my bend will be automatically calculated because of the formula inside. Then we can use this top edge to create another flange, and we could actually define create flange with width as such, and you'll be able to define an offset distance like this, for example, or you can press tab and you're able to use the dynamic dimensions to define the longer length or the shorter length of the flange. For example, over here, we can now say 30, for example, like that. And on the other side, we can also define a particular distance. So this is how you could also create a flange on the other side. So let's say even on the other side, I want the distance of 30, and whereas the length I actually want is roughly about 65, for example. Okay. And there you go. All right. So now we'll look into, for example, if I have this solid face over here, I could switch the relief pattern. For example, we can switch to a round relief, and you can see that this round relief will be visible over here. And you could also change the relief back to a smooth relief if you would like to change it to this way. So depending on what you would like, you can use different relief patterns. For example, you can switch to a rectangular relief pattern, which we will stick to. All right. So then we will use this edge to create another flange and use 30 mm as our distance. Okay. And now you could actually click on this particular surface, and over here, you can see the quad cursor will give you various options. In this case, we will use the rotate flange option. In the rotate flange option, you can post modify your flange, and you can define what angle you would like to have. Okay. Similarly, now if I decide to make a change, I could also use the direct modeling functionality of push-pull. For example, over here, I can directly push-pull behind by 60, and dynamically my design will update. Okay. All right. So now all these changes that we're doing, these flanges that we're making, are directly recorded inside the mechanical browser. And after this, if I decide that I want to change the thickness of my sheet metal, I could go to changing the entire sheet metal thickness from 2 mm to, let's say, 5 mm, for example. And you can see this automatically getting updated. Okay. The other properties that you could change inside the properties mechanical browser dialog box is, for example, defining the type of bend radius calculation you would like to have. Would you like to have it as an obsolete value or a thickness ratio? In this case, we can keep the thickness ratio of 1, or I could change, for example, the thickness ratio I could change to 2. So you can say that my bending radius will automatically get updated based upon the thickness ratio. Normally, 1.5 is quite a standard in the industry, so we could stick to 1.5. And we could also look at the bend relief. For example, you can define if the bend relief has to be obsolete value or a thickness ratio. Similarly, you could also define a K factor, hem relative bend deduction. These are all the functionalities, the editabilities inside the properties that you can do in the mechanical browser. Also, you could select it feature by feature. For example, the bend relief, the flange 4, flange number 2 can individually be selected. Okay. Now let's look at editing this flange and this flange together. Okay. So we have selected this flange, and then what we would like to do is actually use the feature. Either I can match the length over here, or I can change the length. For example, let's change this to 60. Okay. And again, the angle can be adapted. Over here, you can see that the reliefs are created, the junction, and we can actually go to this particular face, and the quad cursor will give me the relevant functionalities. Like in this case, I would like to switch the junction and then have the junction to be made like that, overlapping each other. Okay. All right, so we can actually do this on both the sides. So we can actually select this line here, can select this line here, and we could directly give the same, we could have the same behavior for both the flanges like that together. So let's choose for a length of 60. Okay, and the angle we can stick to the same, right? And then do the same on this edge over here, and we'll do it on this edge over here. And then choose another flange. Let's say in this case, we will use 40 as this edge over here. Okay, there you go. So both flanges will be simultaneously created. Now what we can do here is we could continue building our sheet metal design. For example, let's say this is, you want to hook this or slot it onto a particular element or a component. We can have slotted holes. So we could actually go to our hole library, so standard parts and inside sheet metal library, you'll find form features, for example, or you can also directly go to holes. Inside holes, you can use a slotted hole, and the slotted hole, you can directly place it right in the middle here. And below you can see the command line. You can actually rotate this, rotate it, okay, and then position it in the center over here. Okay, so once you position this, you could also now after that edit this particular slotted hole. The properties of this slotted hole can directly be edited. For example, the diameter, instead of 10, I could make it 15, for example. But in this case, we'll just stick to the diameter of, let's make it smaller, 8, for example. And the length, we could make it 40. Okay, and there you go. We have a slotted hole now, which is sufficient enough for us. And the depth, perhaps we just reduce down to 10 so that our slotted hole doesn't project too much outside. And then I can mirror this slotted hole on the other side. So I could actually switch to the back view, okay, like that. So very easy. The view cube can be used to switch on the back view. And you could now mirror this by simply typing in MI, mirror, and just use a midpoint over here. Okay, for example, like that. And then enter there. Okay, there you go. Just switch it off. Let's go mirror direction, for example. Okay. Okay. And then we have mirrored this on the other side as well. And the slotted hole has been transferred automatically. Now let's add some punching holes on top of this. For example, over here. Okay. So for that purpose, we will simply insert, and we are going to insert a 2D drawing. We will insert the holes 2D file, which is just a 2D DWG file. You can open it, and then you could insert, and the insertion point could be specified on the screen. Just bring it in here, and we could just place it on this face, for example. So I'm just going to rotate this, for example. Okay, just UCS world. Let's keep the UCS down and let's insert it again. Okay. Let's insert the file again. Just insert it. Okay, here we go. So we can just position it like that here. There we go. So we have these punching holes. You could select all of these holes. For example, this is simply 2D line work. And we could simply extrude these and cut a hole in our sheet metal, for example. There you go. So this is your hole in the sheet metal. Now what we can do is further we can explore the chamfering features. For example, we're just gonna use these edges, all the edges, we can select them. Just select the edges over here. This one, okay. And we could also select this one. And select this edge and this edge, okay. And here, for example, now you can see that the quad cursor will automatically enable the chamfer feature. So this is the machine learning inside BricsCAD, which actually reads the user behavior, reads also the functionality that you're using. It understands that it's a sheet metal and you are now looking at chamfering. So it'll automatically give you an option of chamfering. And after that, you can choose to use the chamfering feature and just give a chamfer value of 5. And the chamfer will automatically get created on all the edges that you identified for. Okay. We can choose this edge and same chamfer will appear. The quad cursor will understand that you have actually instructed in the previous command that you would have to do a chamfer, for example. And in this case, we will also initiate a chamfer, for example, of 20. And then further to modify this chamfer, what you could do is you can actually select this surface and simply use the push-pull to actually match the edge over here. And there you go. Beautifully, you can just create this edge like that. And post that, you could now switch the junction type and lock or close this connection like that. There you go. So this was sheet metal from scratch. If you would like to add some form features in this, please feel free to do so. We will explore it in another option. Now after this, what we can do is, let's say I'm happy with this design and I would like to test it out, or I would like to directly go and cut it out into a CNC machine. So what I would do is I'm just gonna unfold it, or I can directly export to DXF, or I can create an associative unfold, which you will be able to see the behavior immediately. So I can unfold, simply select the face, and there you go. I can unfold it directly over here. And my unfolding pattern will be created directly. And it will give you the dimensions and also the annotations for the bend and how much degree of bend and what is the bending radius associated with the degree, which your CNC machine will be able to read. Now, important thing is here that you can export to DXF directly. So you could select this particular sheet metal and you can directly export as a DXF. And over here, you can see immediately that at my fingertips, I'm able to get the area, the perimeter of that particular piece or part of the sheet metal. Okay. And here, now you can directly send this to your CNC machine. If you would like to control the settings of your export of the sheet metal, then in your settings, you can go to sheet metal and the feature colors can be identified, for example. And what are the other commands, let's say for assembly export. So all these colors can directly also be checked. Layers for unfolding, for example, what is your target cam? Okay, you could actually insert a particular value over here or an extension. The contour layer, the color you can change. The bend lines color you can change. The bend line down layer, overall dimension, bevel features, what color you would like to show bevels as, form features, how would you like to represent them. However your CAM system is going to read it, you can set this up for export. Yeah. Similarly, your OSM exports, you can also change the factors of accuracy and minimal edge length. These can also be changed. So that was unfold. And now let's say you have a solid model. Yeah. Let's say you have a solid model, something like that, and how you can convert it. So let's say you just receive a solid model like this, like a block model, and this is what you're now going to convert into a sheet metal. So for that purpose, what we can do now is simply use the shell command. Okay, the shell command enables me to create a shell out of this solid, and you can just give a thickness as a shell offset, and that's it. So for example, now you have a shell. Now this shell you can convert to a sheet metal. So now I can convert to sheet metal. Just use this command and choose this face, enter, and there you go. My entire sheet metal will begin over here. So a simple 3D solid that you just used by push, pull, and extrude modeling could be converted. Then we could directly start by adding reliefs. For example, I could create reliefs in the entire model, and there you go. I have my reliefs over here, for example. So just before the reliefs, what we'll do is we'll create a feature over here where we can just edit the sheet metal by adding an offset of, let's say, 15 over here. Okay, and then just would like to remove this portion and create a hole over there. Simply extrude back and just use a value of 10, and there you go. So now I have this feature that I would like to add to my sheet metal. Okay, let's say it's a countertop, and here you want to insert a glass or a acrylic sheet as part of your digital monitoring system, something like that. So after that, we can now do the reliefs again, create relief for the entire model. Just press enter, create the reliefs. Okay, and further to that, we could start adding junctions. So just create a junction. So let's say create a junction here, 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 and here. Okay, and here, right? So similarly, we can create a junction here, 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 and here. So reliefs will help us in controlling how our junctions get penetrated into the system, for example. And after this, we can actually start creating bends. Create bends, create a bend here, create a bend here, okay, create a bend here, okay, all right, and create a bend here, for example. There you go. So your bends are ready, right? And the next thing, what we can do is, I'll just open this model over here. So after creating the bends, for example, we could now, let's say I want to actually split this because it's, so let's say first we unfold it. Yeah, let's unfold and see what's the size of this unfolding. So just gonna unfold this body, select this particular face and unfold it. You see that there is actually a clash, and probably we would have to split this panel into few pieces. Let's say we would like to split this into 2 pieces. So in this case, what we can use is split by point. So simply split the sheet metal and just select this part to split. And you could use a machine learning feature inside BricsCAD called propagate to transfer this split to the other corners. So this is AI at its best. So for example, now if I choose this corner, you see that there's a design assist suggestions that are provided to you. Would you like to apply this split on these corners as well? And you have a choice. You can actually choose to apply in different ways, for example, left or right, for example. And you could also choose not to apply here. Let's say I don't want to apply it here, but I could even apply it. Let's say afterwards you decide, yes, I want to apply. And after propagating, you simply enter and your sheet metal has been split into two parts now. So you can see here that there are two bodies. So we go to the mechanical browser, okay? And just a second, I think I need to sign out of my Teams. Okay, so we have two bodies over here right now, body 1, for example, and body 2. So let's say the body 2, I would like to have a different wall thickness, a different thickness for my flanges. So I could go to body 2 and switch it to a solid, a contextual solid thickness. And then I can edit the thickness from 2 mm to 3 mm. And then this particular sheet metal piece, which is another part, will be thicker. You can see here, for example, is thicker. All right. And this one has a different thickness, and that one has a different thickness. Okay. So now I could unfold this portion separately. Enter. And I could unfold this portion separately. There you go. Done. Okay. So now I could meet the nesting requirements. For example, you could simply use a rectangle or do manual nesting, or maybe use a nesting software, free nesting software to do so, to check the sizes. So now it's fitting into my particular size and I'm good to go. I could directly export it out to DXF or batch export and send it to the CAM machine or CNC. Okay. So the next feature that we are going to look at is, all right, so let's actually now start a new drawing again, a new model, which is a mechanical template. And we would, in this case, be importing a file that was created in SolidWorks. So we're going to import a SolidWorks part file, which is a sheet metal enclosure, which was done for a CPU, or it could be any gadget, for example. So you can bring in multiple formats, like I mentioned before. You could bring in Solid Edge, SolidWorks, Inventor, Creo, IGS files, step files. You can bring them in. Rhino models, SketchUp models, all can be bought inside BricsCAD. So you could now, let's say, bring in a SolidWorks part, sheet metal enclosure, open it, and give BricsCAD a few seconds to digest the information, and you should receive the model inside. So below you can see we're getting this update bar. Now we are importing the sheet metal inside. Okay, so there you go. My background import has been finished, and I could now open the sheet metal part, which was created in another MCAD software. And here you go. This is now a simple 3D solid. Yeah, if you go here and check it out, it's just a 3D solid. It's imported as a 3D solid. There is no assembly information. It's a regular. The material has been captured as alloy steel. The physical properties have also been captured. So the material information has been transferred, the geometrical information has been transferred, and now within BricsCAD, we can beautifully convert this to a sheet metal, right? Convert to sheet metal, just click on one of the surfaces and just choose entire model. BricsCAD will use the 3D geometrical information and intelligently convert it to a sheet metal. There you go. We see that there are some form features, like ventilators, for example, or some other form features which you see here. So let's convert them to native BricsCAD form features. We could simply hover our mouse to that particular form feature, and here we have an option of replace form feature. So replace form feature can be utilized to convert the standard form feature to a BricsCAD form feature, such as louver, for example. So just open the louver form feature, and in this case, there's an option below, replace all similar form features. I would select yes, and similar louvers will be identified inside the model, and all of them will be converted to native BricsCAD form features. There you go. This step is important, otherwise you will have some errors when you're doing unfolding. So you have to convert your SolidWorks form features to BricsCAD form features by simply replacing the form feature. In this case, it's an emboss with a hole. Yeah, so this is simply an emboss with a hole. Again, yes, to convert all of them, and there you go. This is now converted to a BricsCAD form feature. Whereas within BricsCAD also we have form features that you can use. For example, or you can create your own form feature. For example, if you want to create a rib feature, you could simply go here and let's just create a circle. Just going to create a circle here, 40, okay? And I can create a rib feature, create rib feature, select flange face, select control curve, and yeah, I think I need to profile radius, just give a radius of, let's say 1, okay? Okay, there you go. There you go. And here you have created a rib feature, okay? So you can create them from scratch, or you could just bring in a standard feature, which is, let's go to sheet metal form features, and you can choose any of these form features, and these are all parametric. Yeah, so if you want to bring in this dimple or an emboss or such a form feature or a bridge or an emboss like this with a hole, so let's just bring in a dimple, for example, and we can place it over here. For example, just place it here, okay, and it's automatically considered as a form feature over here, and the rib is also considered as a form feature. All right, so these are parametric, so you can actually go to the particular form feature by going to the mechanical browser, and you will find all of them here. So let's call this, you can see this dimple, even the emboss, you see the values over here, the parameters. You could go to the dimple, and for example, over here, the diameter I can change from 8.89 to 12, for example. There you go. Or let's use a bigger value, 18, and it should automatically change. And we can go back to 9 if you would like to. So all these are parametric, and they're automatically connected to your sheet metal parametrically. Okay, so now we can do the unfolding for this sheet metal part. There you go. Your unfolding is here. Took, enter, and you're ready to go to fabricate this part. That's it. Or you can export as a DXF. All right. So one or two more things that I would like to show you guys is lofted sheet metal. So lofted sheet metal is also a nice feature, and tabs, right? Two features. We'll show you tabs and lofted sheet metal. So let's say you have yeah, a rectangle. Okay, just draw it any size you want. just draw, for example, 190 by 200, okay? And you have a circle that's, yeah, maybe 100 radius. 100 is a bit too much. We can reduce it a bit, make it a bit smaller. There you go. And simply move it up here by 200. There you go. And now we will use the sheet metal loft. So let's go to sheet metal loft. Click on the curved bottom, the rectangle, and click on the circle here and give it a particular thickness. So what's the thickness? Let's check the thickness. It's 2 mm. Maybe I want to change it to 3. Okay, and there you go. So here you go. You have your sheet metal part. Okay, and from this, I could actually now go to the body here, and I could change the thickness from 3. If you want to make it 5, you can make it 5 and change it also. All right, so we have discussed these features, and now what we can do is, for example, we can also look at a tab functionality, or let's do it this way. We create a rectangle over here, for example. All right, and then we can use the base flange feature to simply create a base flange like that. Okay, and we will choose the top curve, enter, and your base flange is ready. And let's say now I use the bend feature. So let's use the flange bend feature, flange bend, and we select the face. Okay, this flange bend side. Maybe we just draw a new line. Okay. Okay, and there you go. I can now use that line as a guide to follow my bend over here, for example. And then let's choose an angle of 120, for example, or let's just go to 90 because we want to show the tab feature. And there you go. Right? So for the tab feature, what I would like to do is we can now convert this particular bend. First, I'm just going to hide this, and we can convert this bend to a junction. So just select this and we convert it to a junction. Okay. After we convert it to a junction, we can now use the tab feature, create array tab, and just select this face, and you have an array tab over here. We just press enter, and then after that, we can go to the tab over here, and below you see the tab properties. So the number of slots we can change from 2 to 4, for example. Okay, so let's just change this to 4. Okay, and we could now the distance, if you want to change the distance, we could also do that as well. So over here we have other options as well. Okay. So, well, there are other features. Feel free to explore the sheet metal inside BricsCAD. I think I've covered almost all of the features. We do encourage you guys to download BricsCAD, and when you download BricsCAD, just download it from any the website. For example, you could just go to BricsCAD, for example, just go to brics.com, and brics.com, you can download BricsCAD from the website and test it out for yourself, and just log in, and you can just sign up to download. Once you sign up, you directly can download the latest version of BricsCAD, and there you go. And for any tips and tricks, you can directly go to the BricsCAD Help Center. In the BricsCAD Help Center, for example, if you simply go to bricscad.com, here you can go to Learn. In Learn, you can go to YouTube channel, or we have webinars, we have a blog, we have help and documentation. The help and documentation is very helpful. Or you can go to the BricsCAD YouTube channel. In the BricsCAD YouTube channel, you can go to BricsCAD Mechanical tutorials, and inside BricsCAD Mechanical tutorials, you will have a lot of information that you can use for your learning. So happy exploring, and with this, I would like to thank everybody. It was great presenting to you guys today, and a lot of participants we see, and also good response on LinkedIn as well. We have seen, so keep following BricsCAD webinars. We will keep doing more. You can go to the BricsCAD LinkedIn channel and subscribe. You will get to know our latest webinars as well. And thank you very much.